In this video, we'll build on the discussion from last time to explain how to integrate lots of things of the form some power of sine times some power of cosine. Remember, the big idea in the last video was to take either one power of sine or one power of cosine and put it together with the dx in your integral, and then apply u substitution. And in the second example we saw, we had to use this identity that sine squared x is equal to 1 minus cosine squared x to rewrite an integral in terms of x as 1 in terms of only u. And we could use a more general version of that to say that any even power of sine can be written as 1 minus cosine squared x to a power. So you can take any even power of sine and write it just in terms of cosine. Same idea, any even power of cosine, you can write it just in terms of sine. So our goal in this video is going to be to understand how to solve a bunch of integrals of the form the integral of sine to some power, nth power, times cosine to some other power, mth power. And the first case we'll talk about is when one of these powers is odd and the other one is even. So let's start with an example. Cosine to the 5th power times sine to the 6th power. What are we going to do? Well, let's first note that 5, this is odd, and 6, this is even. So we're in the case where one of our powers is odd and one of our powers is even. So what we're going to do is borrow one of the cosines from this expression, cosine to an odd power. This is the same as cosine to the 4th x times sine to the 6th x times cosine x dx. So what do I mean borrow one of the powers from this cosine to the 5th? I mean, there are 5 cosines here. It's cosine times cosine times cosine times cosine 5 times. And what we're going to do is take one of those cosines and put it together with the dx. Why are we going to do that? Because we're now going to set u equal to sine, so that du equals this cosine x dx that we have here. So what is our integral equal to now? Well, we have cosine to the 4th x times u to the 6th du. This would be a problem if we were not able to rewrite cosine to the 4th as something involving u. But we know that cosine to the 4th is equal to 1 minus sine squared squared. So we know that cosine to the 4th x equals 1 minus sine squared x whole thing squared. So this is equal to 1 minus u squared squared. I'm going to pause and erase and then write down the rest of this integral. First, just as an integral involving u, we'll compute an antiderivative just using the power rule, something simple, and we'll substitute back to get an answer in terms of x. Here's where we were. We want to understand the integral of cosine to the 4th x times sine to the 6th x times cosine x dx. We set u equals sine x, and we have an integral cosine to the 4th x times u to the 6th du. And we know we can rewrite cosine to the 4th x as 1 minus u squared whole thing squared. So where does that leave us? We rewrite this integral just in terms of u, 1 minus u squared squared times u to the 6th du. It's easiest to deal with this 1 minus u squared squared by just squaring it out. We get 1 minus 2u squared plus u to the 4th, all times u to the 6th du. We distribute this u to the 6th and write this as a sum of 3 integrals. The integral of u to the 6th du minus 2 times the integral of u to the 8th du plus the integral of u to the 10th du. Each one of those powers of u, it's easy to write down an antiderivative. So we get 1/7 u to the 7th minus 2/9 u to the 9th plus 1/11 u to the 11th plus c. And the last thing is just to substitute back in that what we're looking for is an integral in terms of x, not in terms of u, So every time you see a u, just put in a sine of x. So this strategy works anytime your first power, one of your powers is odd and one of your powers is even. You borrow from the odd power, like how we took a cosine x from the cosine to the fifth x, and you put it together with dx. And then you let u be equal to whatever the sine or cosine is in the even power. And at some point, you often have to do this thing where you have an even power of one of these functions and rewrite it in terms of just the other one. So an even power of cosine, you have to rewrite in terms of sine, or an even power of sine, you have to rewrite in terms of cosine. So that explains how to do one power being odd and one power being even. I'll pause for a second, and then I'll move on to the next case, which is what to do when both of the powers are odd. The next case we'll discuss is what to do when both your power of cosine and your power of sine are odd. Here's an example problem. Cosine cubed x times sine to the fifth x. What did we do in the last example? We had one odd power and one even power. And we borrowed from the odd power and took a sine or a cosine, depending on which one is the odd power, and put it together with the dx, and then applied u substitution. So here, what we're going to do is, again, borrow from the odd power and put one of the sine or cosine together with dx. So for example, you could write this as the integral of cosine squared x times sine to the fifth x times cosine x dx. This cosine x dx works great for u substitution if we let u equal sine x and du equals cosine x dx. Because now our integral is the integral of cosine squared x times u to the fifth du. And we know we can rewrite cosine squared x just in terms of sine. This is the integral of 1 minus u squared times u to the fifth du. This is just like the previous case. We can write this as the integral of u to the fifth du minus the integral of u to the seventh du. And this gives us 1/6 u to the sixth minus 1/8 u to the eighth plus c. And you can now substitute back in 1/6 sine to the sixth x minus 1/8 sine to the eighth x plus c. OK, it's just like the last case. You take one sine or cosine from an odd power and put it together with the dx. But what's different here is both sine and cosine are being raised to an odd power. So what if we had chosen the other one? Like here, we borrowed a cosine from cosine cubed to put with the dx. But let's just do this integral another way, where instead of borrowing from cosine cubed, we borrow from sine to the fifth. So this integral is the integral of cosine cubed x times sine to the fourth x times sine x dx. And now, if we let u equal cosine x, then du equals negative sine x dx, which is almost what we have right here. So what we get is negative the integral of u cubed times sine to the fourth x du. And we know we can rewrite sine to the fourth just in terms of cosine. It's 1 minus u squared squared. So we get negative integral of u cubed 1 minus u squared squared du. And just like earlier in the video, I'll expand out this 1 minus u squared du. We get minus integral u cubed 1 minus 2u squared plus u to the fourth du. So this is minus integral u cubed du plus 2 times the integral of u to the 5th du minus the integral of u to the 7th du. I'm going to pause and compute the rest of this integral and explain how it's the same as this answer that we got before. We're trying to compute this integral minus integral u cubed du plus 2 integral of u to the 5th du minus the integral of u to the 7th du. Computing an antiderivative of each of these functions is pretty easy. So what do we get? Minus 1/4 u to the 4th plus 2 over 6 u to the 6th minus 1 over 8 u to the 8th plus c. And we just substitute back in a cosine everywhere we see a u. And we get minus 1/4 cosine to the 4th plus 1/3 cosine to the 6th minus 1/8 cosine to the 8th. And that is the integral that we started with, the integral of cosine cubed times sine to the 5th x dx. But we already did this integral before, and we got an answer that looks different. So what does that mean? Well, we have a constant here and a constant here, because when you take an antiderivative, if you add a constant, that doesn't change anything. So one thing we can do is move all of the cosines here over to this side and move the constant here to the other side. And what that means is the function that is equal to 1/4 cosine to the 4th x minus 1/3 cosine to the 6th x plus 1/8 cosine to the 8th x plus 1/6 sine to the 6th x minus 1/8 sine to the 8th x. This function of x is equal to a constant, that it doesn't actually vary with x. So this is very not obvious. What you would have to do to see this is factor some of these expressions, like cosine to the 6th minus sine to the 6th. Well, there's a factor of cosine squared or cosine cubed minus sine cubed, things like that. Some like tricky trig stuff. The point that I'm trying to make is we started with some integral that was the integral of cosine cubed x sine to the 5th x dx. And remember, the big idea is we want to borrow from one of the odd powers a sine or a cosine and put it together with the dx. If you borrow a cosine and put it with the dx and then let u equal sine, then you get one expression for this integral. If you borrow a sine and put it together with the dx and then let u equals cosine, you get another expression for this integral. Both of them work. They're about equally difficult, and you just have to make a choice and go with it. So when both powers are odd, there are two different ways to make the u substitution work. And they'll lead to answers that are both correct, but maybe not obviously equal to each other.